Hello, IB. We are looking at 12, B1, and B2 in this video, so make sure that you actually watch through both B1 and B2, and there are a couple questions for you to try in between as well, so you can pause as you go. But I mentioned this in the last video, that we are now going to look at different pathways to put two vectors together and end in the same spot. So I could have two different paths in order to get from A to B. So here we just have an example of what some of you guys might draw. So if you want to pause here and see what you would draw, if you have a person who's leaving town P to go to town Q, 40 kilometers away, and then to town R, 60 kilometers away. So this is two different steps of the path. If you pause here, go ahead and see what you guys would draw. For me, I'm going to start with P, and we have our first vector from P to town Q. And that was 40 kilometers away, so I'm going to label the magnitude as 40 kilometers. And then we have a second vector. It's going to take us from Q to R. And that one is 60 kilometers away. And you might have gone down, you might have gone up, you might have gone left, whatever direction that you went when you drew your own vector. Just consider the fact that wherever you start and wherever you end, we are going to end in the same spot. So I could have also walked in a straight line and just said, I walked 40 kilometers, here's Q, I walk another 60, and here's R, okay? So wherever you guys are, the shortest path, obviously, would just be going straight, boom, right across. Now here also, take a look at what we just came up with, because we have this triangle, so possibly there could be a trig question where you guys would need to find the angles or the bearings of the direction of travel. So just remember that this can now be kind of folded into other topics that we've already done. What you guys are creating though here is a resultant vector. So this vector that we finish with, so no matter what direction you travel in, the vector that takes you from your initial position to your resulting position is called your resultant vector. So wherever you are, and whatever path you take, a straight line from your start to your finish is called your resultant vector. So that would be vector PR, okay, going from start to finish. If you think about displacement, we've been displaced from P to R. However, if we walked 40 kilometers and 60 kilometers in a triangular shape here, we might have, from P to R, the displacement could be a lot shorter than actually traveling 40 kilometers and then 60. So the most we could walk is 100 kilometers, but remember we could walk less than that. So try to think about what would be the shortest distance traveled to get from P to R. Okay, and this is a non-right triangle, so you can start bringing in different topics in trig and think about what you might need to do to find this minimum distance from P to R. When you guys are adding vectors together and getting our resultant vector, we always want to have tail to tail and head to head. So when you guys start at P and start your travel, when we do our resultant vector, we start at P again and we end at where we finish. So the arrows will match up here and our beginning points will match up here. So tail to tail and head to head when you guys are drawing that resultant vector. So because we do need a scale, and just to practice drawing vectors with some kind of relation to a scale, we're going to take a look at our vector A given to us here, which if we take a look at it, we've from beginning to end, we've moved 3 units to the right and then up 4 units to make vector A. To make vector B, we start at our tail, we go 1, 2, 3, 4 units to the right and then 2 units down. So when we're asked to add vector A plus vector B, what some people might do, they might take vector B, and if you start with A, we now add on vector B. So I need to make a vector that's exactly like this one. So that means I'm going to look at how many units I travel right and how many units I travel down. So 1, 2, 3, 4, down 2, and then I have this vector that finishes right here, and that is equal to vector B. So I've traveled 4 units right and 2 units down. So it's the exact same vector that I just picked up and relocated so I could join arrow, right, head to tail. So arrow to our beginning point for our vector, our initiating point and our terminating point. If you guys then have a resultant vector, we have started at A, we end at B. So here is our resultant vector. Now somebody else might have come along and thought, well, if I can add vector A plus vector B and get my resultant vector A plus B, why couldn't I start with B and add A and get resultant vector B plus A? Are those the same thing? So when we add, remember when we add, the order doesn't matter. So what would that look like visually? If we took the same vector B, but instead of adding it onto our arrow end, our terminating end, we add it onto our origin. So we'll go again, it's right 4 and down 2. So I am going to take left 4, so 1, 2, 3, 4, and then up 2. I have to travel in the same direction, so I still have to have my arrow coming down this way. And then this would be my vector B. So is it the same length, and is it going in the same direction? Yes, it is. So if I take B plus A, I'll end up with this resultant vector that looks something like that. And instead, this would be B plus A instead of A plus B. So does this green vector that I got with B plus A equal vector A plus B? So is it the same length, and is it traveling in the same direction? Yes, it is. So again, we've got multiple ways of drawing how to construct putting 2 vectors together, just because we are looking at, again, direction and magnitude. So there's more than one way to actually demonstrate that. So just to guide you guys in a direction to take a look at example 4 and then question 4 in that same section B. Take a look at both of these questions, and we are going to start our discussion with this one. This number 4 here, where you have to prove the associative property, is actually an interesting one that you're demonstrating visually. So with those two, try both of those out, and we'll start our discussion with those. Again, this is B.1, and we are going to go straight into B.2 here. We also left you guys at the end of the last video thinking about whether a 0 vector exists. So if we think about what a 0 vector is actually representing, we need to have some way of describing a resulting movement in an opposite direction. So if you have A plus the exact opposite of A, we have really been displaced nothing, no distance. So you're actually just traveling back, and you would wind up getting 0. All right, so we will have a 0 vector just to describe that situation happening. So vector subtraction is B.2. So similar to vector addition, just like when you guys learn how to add integers together, if you're adding a negative number, we say subtracting. So if I'm adding a vector A plus negative B, we basically are saying A minus B. So be thinking about that same idea with vectors. However, now we have a direction associated with vectors. So if I'm asked to discuss R, vector R minus vector S, we have vector R here to start. And if I added S, I would just join. I just terminated at this arrow end. So I would start with the originating end, tack it on to the arrow end, and then go in the direction of S. So I'd have all of my arrows in the same direction. But since I am subtracting S, I can take the arrowhead and match it up with the arrowhead. So then it would be R, and if I continue to travel against the direction of S, then it would be minusing or subtracting S. So if I did that, I'm traveling 1 left and then down 3. So here's my S vector. And if I started here and ended here, then I've traveled R minus S, and this would be my R minus S vector, because I've traveled against the direction of S. Now, similarly, because we know that we are adding the opposite when we subtract, I could also do this situation where instead of having my arrow at this end, I keep my arrow at that end, but then I call this vector negative s. So then when I add these two vectors together, so r plus negative s, I wind up with my resultant vector of r plus negative s, which is also just r minus s. All right, so think about how integers are added and subtracted, because we're going to work with our vectors this very similar way. So think about what you guys might do to model s minus t minus r. So if you put three of them together, try to figure out how you might model that using your vectors. All right, guys, we're going to leave you there for vector subtraction, and we will pick up with B.3 and 4 in the next video. Have a good night.